All right. Are we live? Right. I see my own video. What's up, guys? I took a break yesterday. A well-deserved break. My ass hurts sitting on this chair all day, every day. And my eyes have also been acting very funky. I don't like that at all. I'm growing old and I'm still fucking broke. This is not the plan. This is not how it was planned at all. And today, unlike my other streams where we solve questions, I mean, I do like solving questions, but that's only when I can solve them. We are gonna learn some data structures, right? Because I found myself getting very intimidated by topics like graphs and DP, and sometimes in coding, well, in like random questions, or if I have some sort of interview coming up, if I do, lucky me, well, if I see a question and I feel like this is gonna take dynamic programming, or this requires graphs, or this requires union sets, or just some sort of data structure that I have no idea how it works, then I stare on the screen blank. I can't. I mean, you can obviously say you'll just use a hash map to every single fucking question on LeetCode, but that's not the most optimal thing to do. And so I have decided that today I'm gonna. What the fuck did I just say? Today I'm gonna clear my fucking tabs out first, is what I'm gonna do. Right. I was learning about React server components and error boundaries and all that good stuff. Man, there's a lot of good shit open right here, but I need to close it. I can. Oh god, what the? Yeah, that's fine. Excali raw, 3 sum is open. Well, the lead code, 3 sum question. I did practice yesterday. It's not like I didn't do anything. I did a few questions on my own, revised a few questions from earlier, did a few questions from arrays, finished that majority element question that we were doing in the last live stream, and peek on what is up with my screen. Right, there you go. I'll pop the chat out very quickly, put it on my other screen. Right, that's got that sorted. Put that right over there so I can watch you guys chatting if someone wants to talk to me. And I'm just gonna see my eyes. They're acting all funky and I get all blurry vision. Dude, you sound kind of funny. Do I? Do I have the right? Do I have the right input? Let me just check. I think I do. Why do I sound? Why do I sound funny? Well, check. WP, is that WhatsApp? Yeah. Okay. Go ahead. Mm-hmm. Let me just. Maybe it's. I don't know. I tried plugging it out and then plugging it back in. Is that better? Or maybe you're just used to me deepening my voice and talking to you guys like this, like every guy should, and you just got used to it. Right, William said data structures and algorithms. This is gonna be a lot of me churning out videos of William said. This is a really nice playlist, is what I'm gonna say. I've got it downloaded on my phone, and every time I'm in the metro, I just, you know what's up. Right, every time I'm in the metro, this is exactly the thing that I'm watching. And I'm not logged in with the right account, so I have lost all progress of where I was. But what I'm gonna do is I'm gonna try and implement the data structures. Right, this guy is an ICPC World finalist, and that means in all sense of the word, ICPC World Finalist, is a man you should be respecting. Introduction to Big O, abstract data types, dynamic and static arrays, dynamic array code, linked list introduction, doubly linked list, stacks implementation. I can do stacks implementation, right? It's just push, pop. Uh, do I wanna, well, I wanna do one. Let's see. How are stacks implemented internally in C++? C++ stack is implemented using a container adapter. By default, it uses deck as its underlying container, which can also be implemented with vector or list. Stack adapts the interface of these containers to provide stack-specific operations. The fuck is a container adapter? Special type of container class that they are not full container classes on their own, but wrappers around other containers, just vector, deck, list, queue. Okay. C++, STL easy. This article will discuss deck containers in C++. So these are the right linked lists, double-ended queues, and vectors. That's all. We're just saying that the stack uses double-ended queues. Our deck implemented in C++. Using dynamic array of arrays, the structure allows for efficient insertion and deletion. And I don't really, when a deck is created, main array is initialized with a certain number of blocks. Often around it, as elements are added to the deck, the blocks may fill up. Let's see how it, now I also feel sleepy there. Well, it's like 4:40, everybody's supposed to feel sleepy right now. It's the people who are working who don't. It's the day today, it's Thursday. I honestly don't know where time went today. I have no idea. That's just dumb. Dex implementation is dumb. And I see this insect crawling up my walls. I don't know what I want to do with it. Queue implementation, stack implement. Let's look at the stack implementation. Really, I don't think we spend that much time doing that. Oh, well, I need to change the sound. Right, that should work.
Cover how to push nodes onto a stack with a singly linked list. Later on, we will look at source code, which is actually written in a doubly linked list. Okay, to begin with, we need somewhere to start to be in our linked list. So to point the head to a null node. Well, it have one idea or by the first node off the stack and set the node's reference to count. So that will be picked up by the garbage collector plus it is it's pointing out to the screen. Alright, I have to look at this next video, how to get code.
Right, we can just do some C++ code because I haven't coded in the actual language without any LeetCode interface for a while now. I'll do exactly that. And maybe we can have some fun with actual data structures today. Right. I hope this isn't working. Oh, it is. I should. Yes. Um. Ah, yes. Been so long since I actually coded like this. What we're going to do is we're going to create a stack using a linked list, right? So we can create, it's got data, uh, and then as public functions, we're going to implement, I think, right, we're going to implement as well. It's got data and it's got next, right? Let's just say value of this cannot be assigned to an int. Right, right, it cannot. So if I want to create a null pointer, how am I supposed to do it? I don't know, man. You do that, and then that's a null pointer. Is this expected? Right. Is that better? It is. And I think that's it. Right. So if I want to create, what is your opinion on India asking Meta to not show any Pakistani profile in India and then accepting it? That can't be real. That cannot be real. I don't really. It's just fucking weird, vibe. So I create a new node, and then what can I do to a linked list? I can do this, and then okay, I'll just make this public too. I don't fucking care. Why is this a thing? LNX alert is inaccessible. I have to write public. There you go. Is that better? It is. Now I want to create another function that just says, does that work? And then see out and next node data, and I'm gonna send this a value of 8. Does that work? How I implemented my own linked list? I have. It's awesome. Right now, using this linked list that I have implemented, I am going to create a stack. My stack. Right. Um, all gonna be public A, size equal to 0, and so there's gonna be my stack that creates a new this some shit about pasta. Holy shit, that's real. I actually blocked fucking Pakistan. Right. So when we do this, we're gonna create a head, no, a top. All right. And so there's a method called push. It's gonna take an int x. So my bad. So do constructor functions don't need. I'm gonna pull this over here. Open chat GPT. Do construct. See if we require return type. They don't. Right. They don't. They don't. Alright, I don't really fucking care about them banning Pakistan. What I do care about is Meta hiring me as a software engineer. Now that's something I want. That's something I give two shits about. Right, so what this does is basically it's gonna create a new node with some value x, and then node next is equal to top. I'm getting a call from someone. I don't know who. Might be someone from the internship, so I'm just gonna pick it up quickly. Just a second, guys. Hello. Hi, who's this? Hi.
Oh man, one of these days this is gonna be a call from some internship and I'm gonna call back. But it was not. What it was someone trying to get me to buy some property. I've got like fucking not even 4 digits in my account, bro. Not even 4 digits in my account. And can I? No, I need to get it back. Right. Resume my camera and set it up right again. And yeah, okay. Right, it was just some telemarketing. Oh man, I'm so I like this. I like creating my own data structures. This is actually interesting work. Right. So node next is top, and this top is equal to, well, I'm just gonna make it node, and then obviously, just a second, I need to not declare this. This is declared along with here. This size is equal to 0. Right, got it. There's push. There's a method called top, which returns uh-huh. If this top, right. So if its next is a null pointer, then you return, well, you don't actually return anything. You should probably throw an error. Right, it's an empty stack. Throw error. How do you throw errors? Right. So push top and then pop. Right, just gonna check if this top, if its next is equal to null PTR, you shouldn't be, then you again, you're just gonna throw the same error, and if not, then you move on int num equal to this top data star temp equal to top top next delete temp, and then turn num, and obviously size Oh, I can just use size. What am I doing? Again with this, I can just use size. Push, pop, top, size. Push, pop, top, size. And I think that should be it. I'm just gonna ask ChatGPT, is my implementation okay? Couple of improvements and potential. Uninitialized data in default constructor, in your default constructor. You might want to set default value like 0. Okay, that's something nice. Use of member initializer list. Assigning inside the constructor body, C++ style prefers initializer lists for performance and clarity. Data X next nil pointer. Got it. Got it. I completely forgot about these default constructor with data. Oh, did I? Member variable and a method both names are this because the name and content the compiler will likely give an error. Rename the method. Right, got it. Invalidities of default constructors. Push me the top next point to that dummy node. Oh wait. So I create a new node. Node next is pointer at top. Is top equal to no? No, this is an right. My stack is top equal to new linked list. Right. So, but creates a dummy node with data initialized due to your earlier fix. But then your first push will make top next point to that dummy node. This means even when the stack is empty, top is not null pointer. This complicates things unnecessarily. Just initialize the top from null pointer in this constructor. I mean, that is actually okay. Just a second. Someone's at the door. Someone's at the door. I don't know. But she's not answering. It's my mom. Mom, dude, wait. I'm gonna send you this on WhatsApp. Check WhatsApp. Yeah. Okay. Top method name clashes with member top. Legal in C++, but confusing. Agreed. Um, agreed. It's mainly my naming and my logic. I mean, it could be better logic. That's what it's saying. So that's fine. It works. And then Q's introduction, Q's code.
Developers, join us for the biggest AI competition with over $10,000 in cash prizes.
All right. Have a look at some source code. Select the queue and find source code that following link on github.com/my username/data.structures. Also, make sure you have watched and understood parts 1 and 2 from the Q series before continuing. All right, here we are looking at some source code for the Q. So this source code is in the Java programming language, although you can probably translate it to any programming language that you need. So for example, to remind example, it's this variable here of a linked list. This is the Java implementation of a linked list. We also use this in the stack implementation. As you see, the kilo stack implementations are very, very similar. So you have two constructors. One of the an empty queue and another optional one which will create a queue but with a first
So he's creating a queue right there.
This is all like so let's just leave it like that. The next step is the size.
Return the size, public is empty, size is equal to 0.
Because you can't peek anything when your queue is empty. Similarly for poll, this will hold the element in front of the queue.
Let's dot peek first.
Similarly for poll, this will hold the element in front of the queue.
Let's dot remove first. Let's dot iterator.
Adds an element to the back of the queue. I guess I have allowed for elements. So if you don't want elements, just put it this thing in the queue.
It's just a
References to the next node, such as
queue is just another. So here's how I think I'm gonna implement queue. I'm gonna use linked lists again. Right, so you've got this. No, why can I not undo? Motherfucker. Anyways, we've got this node. Nice node. You like that node? I like that node. Right, you get this node. And then you get this node. Well, this is the first node. And some variable points to it. Let's say var. I don't care. And then you form a new node. Head points to this new node. New node. Front points to this new node. Node front points to this new node. Go there. And then you wanna pop, well, this where I need to access this element. So I can move this. So this is bad logic because it doesn't let me do that. New logic. Every new node points here. Right. So we get this in the start, and then new node pointed to here, new node pointed here, new node pointed here. And then whatever the new node is, another variable tracks it. So if we want to add a new one, well, this dot next to this new node and this equal to this one next. So it's just gonna move all the way over here and points to the new node. And when I want to remove, well, I'm just gonna use this variable, get it out of the system, delete this, and probably move it over here first. And then delete it, whatever, yada yada yada. Right. Let's get to it. He's banned. He's banned. Where is banned? So class my queue. Right, we're gonna take care of the naming conventions this time. Make all of it public. Right, so there's one variable ll star front back. And then there's int size. And I think we're gonna start with the implementation. So first we've got the default constructor front null ptr, and then do the same with back, and then this size equal to 0. Right, and then we've got the push method star node equal to new ll data. I'm gonna get data from this parameter, and then if size equal to 0, well, why can't I? Yes, if size is 0, then front, I hate adding this to everything. I'm just gonna copy this over, right? So front is equal to node, back is equal to node, and then I'm just gonna add size plus equal to 1 in the end. Else, right, else what we need to do is we need to add a new node. So back next have this here equal to node, and back I'm just gonna move on to that. And then you add one to the size. Right, that should work. And then we want int pop. Let's just say get front. That's a completely fine variable name, but it's not. Yeah, okay. It's int, and it's basically gonna give you the front of the queue, which is returned. Right. If size equal to 0, throw runtime error. Will it throw new runtime error? No, it's not. Empty queue. Right. If size is equal to 0, you throw a new error. And if it's not equal to 0, well, then you return this front data. And then if it's pop, I'm just gonna make it, no, let's just make it int, so we can make the function a little complex and make it fun. So if, well, easy, size equal to 0, you throw that error. So runtime error for empty queue, and then we can move on. If it's not on, if it's not equal to 0, well, you need to pop, right? Num equal to this front data. Well, I'm just gonna call it front. Can I not just do this? I'm going to just get front, and right, in num equal to this get front. I'm gonna make the front element, and then it's gonna throw an error if it's equal to 0. Well, that means it's not equal to 0, right? So if it's a single element, next one is to a null pointer, right? If size is equal to 0, well then front equal to null. Add this to this thing. Delete temp. and then you return num pop get front, push pop get front, and that should be it. Get size, turn this size. Right, let's ask ChatGPT if that's fine. Oh, my eyes. Look at my eyes, tell me your tale, use the road, the metal soul, tell me the signs whenever the smoke flavor in my face, I'm up with your pocket at the wallet. Pop deletes node before advancing front. I was thinking of that, bro. How did I get it wrong? And it doesn't. Just a second. Right, I got a fucking laddu. Anyways, what pop does is it gets the front using get front. If the size 0, it's gonna return an error and then it decreases the size. And we get a temporary pointer to point to just that front. If size is 0, oh my bad, my bad, my bad. Forgot to write the else case for this. Else. Hmm. Isn't that nice? This front equal to front next. That doesn't need to do anything. Oh, oh no. Just my class, my cube. Thank you. That's better. Uses front data. Increment size. Now size is 0. If I always be true when Q when use cube updating. Keep updating front equal to front next. Even though you haven't updated before, as of now, this front is now updated and there will more than one. The fuck? I'm doing that, bro. Q. Best try to use it until I'm fully qualified. Okay, I think so. Everything works by I've created a stack, a queue, and a linked list all on my own. I created a vector a few days ago. Like, not a few days ago, it's been a while, but I did. I think, yeah, I implemented all of these using a linked list. I don't know if that's the best thing to do, but something I did, so I'm happy with that. I'm gonna go for my class. All the best, Dave. Have fun in your class. Right. Why am I looking at myself? Not this. Where's my... Yes. Priority queue is in production.
What's the fastest way to learn Python?
Not by starting with buddy.
Select the following structure and try to determine whether it's a heap or not. You can pause the video if you like, but I'm just
Well, to be a heap, it should be a tree and it should follow the, no, heap, if I know it's called the heap invariant. That basically means the parent should be less than or greater than all of its childs. Well, its children. So 877, 732, 732, 332, 32, 32. It's got an equal.
No, we have a violation of the heap invariant in this tree, so it's not a heap. Is this structure a heap?
Can two elements, can parent and status. Yes, they can be equal as long as the invariance inequality condition is non-strict. Okay.
Yes, it is a heap because it satisfies the heap invariant and it is true. So we often see heaps like these in what are called binomial heaps. Note that heaps aren't necessarily binary heaps, they have any number of branches. On to our next one. So is this the root to be 10, then the next nodes we explore. Priority queues are really handy anytime you also need behavior in which you need to dynamically fetch the next best or the next worst element. They're also used in Huffman tuning, which is often used for lossless data compression. Many best for search algorithms
I'm
use
getting
queues
cold.
continuously
Just a
get
second.
the next processing node graph as its state first. And finally, we also see priority queues in inference and exponential on graphs. So this is priority is really important, especially for graph algorithms, which is very simple. Okay, on to some complexity with priority queues implemented as a binary heap. But to begin with, there exists a method to construct a binary heap from an order in linear time. We're not going to cover this other than it's pretty cool, and it forms the basis for the sorting out of heaps. Next is polling and, or rather, this method to construct a binary heap from an order in linear time. We're not going to cover this algorithm, but it's pretty cool, and it forms the basis for the sorting algorithm heaps. Next is polling and, or rather, removing an element from the root of the heap. This takes logarithmic time because you need to restore the heap invariant, which can take up to logarithmic time. So peeking or seeing the value at the top of our heap can take constant time, which is really nice. Adding an element to our heap takes logarithmic time, again, because you possibly have to reshuffle the heap by bubbling up the value, as we will see in a later video. Then there are a few more operations we can do on priority queues. So removing an element which is not the root element. So the native way of removing an element in a heap is to do a linear scan to find the item's position and then remove it. Well, the problem with this is it can be extremely slow in some situations, especially if you're removing a lot. But generally, you don't do this, and it's not a problem, which is why most implementations are just, I guess, lazy and do the linear scan solution. However, there does exist a way to reduce the removing time complexity, which I will go over later in a later video in great detail in this video series. So stay tuned for that. This method uses a hash table to reduce the removing time complexity to be logarithmic, which is super critical actually if you're removing as much as we're adding. Now, the ideal method to check containment within a heap, is linear. Again, just scan through all the elements, but with the help of a hash table, we can reduce this to be a constant time, which is super neat, especially if we use the hash table implementation for.
Once removing with help from hash table is login. Naive contains on, contains with help of hash table is on. With some other complexities, binary heap construction is on. Polling is login, peeking is on, adding is o login again. And I did something I shouldn't have.
Overhead, because you're accessing your
Right. Min heaps and max heaps.
Well, here's the problem. Often in the standard library, most programming languages, they will only provide you with either a max priority queue or a min priority queue. Usually it's a min priority queue, which sorts elements by the smallest element first, but sometimes we need the max priority queue depending on what we're doing. So how do we do this? How do we convert one type of priority queue into another type? Well, how we can use is to use the fact that all elements in a priority queue must implement some sort of comparable interface, which we can simply negate or invert to get the other type of queue. Let's look at some examples. So let's for a moment we have a priority queue consisting of elements that are on the right side of this screen. And these are in the min priority queue. So if x and y are numbers in the priority queue, and x is less than or equal to y, then x will come out of the priority queue before y. The negation of this is x is greater than or equal to y. So y then comes out before x, because all these elements are still in the priority queue. First we would get
Converted in.
then let's call
This was greater int.
So that long link to our primary queue with a lexicographic comparator, here's the ordering we should expect. First, the op that, oh, that's all there is to this watching. Well, which we need to go over prior to add elements that filter through our priority queue. However, I want to make this clear. A priority queue is not a heap. A priority queue is an abstract data type that defines the behavior a priority queue should have. The heap just lets us actually implement that behavior. As an example, we could use an unordered list to achieve the same behavior we want for a priority queue, but this would not give us the best possible time complexity.
Agreed.
Concerning heaps,
Got it.
there are many different types of heaps, including binary heaps, Fibonacci heaps, binomial heaps, pairing heaps, and so on and so on. But for simplicity, we're just going to use the binary heap. A binary heap is a binary tree that supports the heap invariant. In a binary tree, every node has exactly 2 children. So the following structure is a binary heap, which satisfies the heap property that every parent's value is greater than or equal to that of the child, that every node has exactly 2 children. Well, then we think the bottom nodes, also known as leaves, don't have children. Well, actually, yes, they do. Here they are. They're the null children in gray. But for simplicity, I won't draw those because they're annoying to draw. Okay. The next important bit of terminology we need to understand is the complete binary tree property. The complete binary tree property means that at every level, except possibly the last, is completely filled, and that all the nodes are as far left as possible in the binary tree. As you will see, when we insert nodes, we always insert them at the bottom row, as far left, to meet this complete binary tree property. Maintaining the complete binary tree property is very, very important, because it gives us an insertion point, no matter what the heap looks like or what values are in it. The next node we insert will go into the hollow circle, and the next one will go to the right of it, and so on, until eventually we fill out the row, at which point we need to start a new row. So the insertion point is very important. One last thing before that, and the next one will go to the right of it, and so on, until eventually we fill out the row, at which point we need to start a new row. So the insertion point is very important. What that means.
Complete binary tree is a tree. Every level, last level, if you complete it with node as left as possible.
One of these binary heaps, and there is a canonical way of doing this, which is to use an array, actually. Last thing, before we actually get into how to add values into our binary heap, is we need to understand how to represent one of these binary heaps, and there is a canonical way of doing this, which is to use an array, actually. So
Can okay, like it's a generally accepted way of doing this is by using a fucking array.
using an array is very convenient, actually, because when we're maintaining this complete tree property, the insertion position is just the last position in our array. However, this isn't the only way we can represent the heap. We can also represent this. When we're maintaining this complete tree property, the insertion position is just the last position in our array. However, this isn't the only way we can represent the heap. We can also represent the heap using objects and pointers and recursively add and remove
What?
tree property. The insertion position is just the last position in our array.
Mm-hmm.
This is the only way we can represent the heap. We can also represent the heap using objects and pointers and recursively add and remove nodes as needed.
Objects and bundles.
But the array construction is very elegant and also very, very fast. So on the left is
Okay.
the index tree to help you visualize the position of each node in the array, and on the right is the actual tree. Remark that as you read elements in the array from left to right, it says that you're pacing through the heap one layer at a time. So if we're at node 9, which is index 0, we're at the top. We're at node 8, we're at position 1, and
2.
as I keep moving along, you can see that we're just pacing through the array going from left to right. So it's very convenient that way. Also, another interesting property of storing
Just a second.
is that you can easily access all the children and parent nodes. So suppose I is the index of a parent node, then the left child is going
Right, I got some tea in my tree for myself. And I'm gonna keep studying because I find this really interesting. This is actually really interesting.
Right child of that node is going to be at 2i plus 2. This is 0 base. If it's 1 base, then you would just subtract 1. So suppose we have node 7, just highlighted in purple. Well, its index is 2, so by our formula, the left child of 7 should be located at 2 times 2 times I plus 1. And the right child easily access all the children and parent nodes. So suppose I is the index of a parent node. Then the left child is going to be at index 2 times I plus 1. And the right child of that node is going to be at 2i plus 2. This is 0 base. If it's 1 base, then you would just subtract 1. So suppose we have node 7, which is highlighted in purple. Well, its index is 2, so by our formula, the left child of 7 should be located at 2 times 2 plus 1, or 5. And if we look at index 5, we expect to get 1, and if we look at the right child, we should expect to get 2 times 2 plus 2, or 6. If we look in our array, this gives us the value of 2. So using this technique, we have all we need to manipulate the nodes in our array. In the source code I will be presenting, in part 5 of the series, we'll see that I use this representation for simplicity. All right, so now we want to... So using this technique, we have all we need to manipulate the nodes in our array. In the source code I will be presenting, in part 5 of the series, we'll see that I use this representation for simplicity. All right, so now we want to know, how do I add nodes to a binary heap and maintain the heap invariant? Because if we add nodes to our binary tree and we don't maintain the heap property, well, the binary heap is useless. We'll do some examples. On the left, I have some instructions which tell us what values we need to insert into the heap. The first value is a 1, which we can see, which should actually appear at the root, since we're dealing with a min heap. But instead of inserting 1 at the root directly, what we do is we put 1 at the bottom left of the tree in the insertion position I was talking about, and perform what's called bubbling up, as my undergrad prof loved to say. This is sometimes called swimming or even sifting up. All really cool names for a really neat operation. So we insert 1 in the insertion position, but now we're in violation of the heap invariant, since 1 is less than 7, but 1 is found below 7. So what do? What we do is we swap 1 and 7, like so. But now we're still in violation of the heap property, since 1 is a child of 6, but 1 is less than 6. So what do? We swap them. But yet again, in violation of the heap property, so we swap, and now 1 is at the root, where it should be, and now the heap invariant is satisfied, and we can stop swimming or bubbling up or whatever you want to call it. So the next one is 13, so as usual, begin by putting it in the insertion position, and now we need to satisfy the heap invariant, so bubble up 13. Notice that we're no longer in violation of the heap property, since 14 is less than 13 and 13 is less than 12, so 13 is actually in its correct position. Sometimes we don't have to bubble up our elements that much. The next values we need to insert are 4, 0, and 10. Try seeing where these end up. Pause the video if you need. It's a good little exercise, but I will keep going for now. So 4 goes in the insertion spot left of all the nodes on its layer, and we bubble it up until we can't anymore, and we stop. The heap property is satisfied. Next is 0, my favorite number. Of course, I've arranged that 0 be at the top of the tree, as you will see. So right now we're in violation of the heap invariant, so let us bubble up. And like magic, 0 is at the top of the tree. Next is to insert 10. The next number is 10, so we put it at the insertion position. And however, this does not violate the heap invariant, so we do nothing. Okay guys, thanks so much for watching. If you're interested in actual implementation of how to add elements, I provide some source code you can look at the link below. In part 5 of this series, we'll be going over the source code in detail. But for now, thanks for watching, and in the next video, we're going to be covering removing elements from a binary heap. Very cool. Hope to see you there.
How does Docker help with production quality applications? And how do you build your own Docker file from scratch?
Welcome back. Today we're going to be looking at how to remove elements from a binary heap. This is part 4 of 5 in the priority queue series. Make sure you watch the last video so you understand the underlying structure of the binary heap. So let's get started. In general, with heaps, we always want to remove the root value because it's the node of interest. It's the one with the highest priority because it's the smallest or the largest value. When we remove the root, we call it polling. A special thing about removing the root is that we don't need to search for its index, because in an array, in general with heaps, we always want to remove the root value, because it's the node of interest. It's the one with the highest priority, because it's the smallest or the largest value. When we remove the root, we call it polling. A special thing about removing the root is that we don't need to search for its index, because in an array implementation, it has position or index 0. So when I say poll, in red, we have the node we want to remove, and in purple is the one we're going to swap it with. So the node in purple is always going to be the one at the end of our array, which we also have its index. So we swap them, we get rid of the 1, and now, since 10 is at the top, well, we're not satisfying the heap invariant. So we need to make sure that the heap invariant is satisfied. So we need to do what's called bubbling down now instead of bubbling up. So what we do is we look at 10's children, 5 and 1, and we select the smallest, and we swap with the smallest. So 10 would go to 1. We need to make sure that the heap invariant also have its index. So we swap them, we get rid of that node we want to remove, and in purple is the one we're going to swap it with. When we remove the root, we call it polling. A special thing about removing the root is that we don't need to search for its index, because in an array implementation, it has position or index 0. So when I say poll, in red we have the node we want to remove, and in purple is the one we're going to swap it with. So the node in purple is always going to be the one at the end of our array, which we also have its index. So we swap them, we get rid of the 1, and now, since 10 is at the top, well, we're not satisfying the heap invariant. So we need to make sure that the heap invariant is satisfied. So we need to do what's called bubbling down now instead of bubbling up. So what we do is we look at 10's children, 5 and 1, and we select the smallest, and we swap with the smallest. So 10 would go to 1. So make sure you default selecting the left node in case there was a tie. So as you can see, 10's children are 2 and 2. They're both equal, so we're going to select the left node to break tie. And now we bubble down 10 again, and now the heap invariant is satisfied. Now we want to remove the value 12. So polling was removing the element at the root, but 12 is not at the root. However, we still want to be able to remove 12. So what we do is we have to search for 12 in our tree, even though we don't know its position yet. So we start at 1, and we do a linear scan through all our elements until we find 12. So 5 is not 12, 2 is not 12, and so on until find 12. And now we found 12, and now we know where its position is, so we can mark it as the node we want to remove, and also swap it with the purple node being the last node in our tree. Swap them, remove the 12, and now we're in violation of the heap invariant, so now we want to bubble up 3 until the heap invariant is satisfied. And now we've satisfied the heap invariant, so we can stop. Now we want to remove 3, same thing as last time, search for 3 in the tree. 3 wasn't far, it was just 2 nodes away. So now, to remove an element, again, swap it with the last node in the tree, drop it. But now the question is, do we bubble up or bubble down the value? Because you don't really know what the value of the node in the last position is when you're swapping it in. So do we bubble up or bubble down? Well, we already satisfied the heap invariant from above, so we need to bubble down 15. So 5 was smaller, so we swapped it with 5. Now 8 is smaller, so we swapped it with 8. And again, the heap invariant is satisfied. Now we want to poll, so mark the root node red, swap it, remove the 1, and now we would want to bubble down. And the heap invariant is satisfied. Now we want to remove 6, so search for 6 in our tree. Okay, we have found 6, and do the swap, remove 6. Now do we bubble up or bubble down? The answer is neither. The heap invariant is already satisfied, so we don't even need to touch our node. We got lucky. Okay, so from all this polling and removing, we can conclude the following. That polling takes logarithmic time, since we're removing the root and we already know where to find it, and also that removing a random node can take up to linear time, since we have to actually find the index of that node we want to remove before removing it. However, if you're as dissatisfied with this linear removal as I am, you would figure out that there has to be a better way. And indeed there is, and I'm about to show you a hack to improve this complexity to be logarithmic in the general case. So stay tuned. Okay, so now we're going to look at how to remove nodes from a heap with the improved time complexity. To do this, we'll need to make use of a hash table, a data structure I have not yet covered, so buckle up, things are about to get a little wild. I promise I'll cover the hash table thoroughly in a later video, but right now it's going to look like magic. Back to the central issue, we have a bunch of nodes scattered across our heap at some positions, and instead of doing a linear scan to find out where the node we want to remove is, we just want to be able to do a lookup and figure that out. The way we're going to do this is that every node is going to be mapped to the index it's found at. So when we want to remove a particular node, we just look up its index instead of doing a linear scan. Sounds good, right? That sounds great, except for one caveat or two. What about if the heap has multiple nodes with the same value? What problems would that cause? Well, just a few, but nothing we can't handle. To begin with, let's talk about how we can deal with the multiple value problem. Well, instead of mapping one value to one position, we will map one value to multiple positions. And we can do this by maintaining a set or a tree set of indices for which a particular node value or key, if you want, maps to. Let's look at an example. Okay, so observe the one value to multiple positions value problem. Instead of mapping one value to one position, we will map one value to multiple positions. And we can do this by maintaining a set or a tree set of indices for which a particular node value or key, if you want, maps to. Let's look at an example. Okay, so observe the blue heap. Remark that it has repeated values. Namely, we can see that the 2 is there 3 times, 7 is there twice, 11, and 13 once. Below I have drawn the index tree, a tree which can help us determine the index position of a node in the tree. 11, for example, is at index 3, 13 at index 5, and the first 2 at index 0. On the left is the hash table with the key value pairs. Notice that 2 is found in 3 positions, 0, 2, and 6, while 7 is found in 2 positions, 1 and 4, and so on. So this is how we're going to keep track of the positions of the values in the tree. If nodes start moving in the tree, we also need to keep track of that. For example, if a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. If a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. And that's it. Okay, so this all sounds great. We keep track of repeated values by maintaining a set of indices of a particular node. The particular value is found out. But now let's ask a further question. If we want to remove a repeated node in our heap, which node do we remove, and does it matter? Because if we look at our heap right here, there's 3 possible 2 values we could remove. Does it matter which one we remove? The answer is no, it does not matter. As long as, in the end, we satisfy the heap invariant. That's the most important thing. So let's look at an example, not just of removing, but also of adding and pulling elements with this new scheme I just proposed. It's not that hard, trust me. So first one, we want to insert 3. So we need to place 3 at the bottom of the heap in the insertion position. We also need to track where the new node is, so we add 3 to our table, along with its position, which happens to be at index 7. Look at the index tree in gray to confirm this. Now that 3 has been inserted, we need to make sure the heap invariant is satisfying. Currently, it is not. So what we do is we bubble up 3. The parent of 3 is 11, which is greater than 3, so we need to swap those 2 nodes. I've highlighted the 7 in the index tree because it maps to 3 in the heap, and 3 in the index tree because it maps to the value 11. Now swap those both in the tree and in the table. Awesome. Now the heap variant is still not satisfied, so do a similar thing for the node above. We grab the parent and do a swap in the tree and the table. And now the heap invariant is satisfied, so 3 has been inserted successfully. The next instruction is to remove 2 from the heap. So which 2 should we remove? Well, as I said, it doesn't matter as long as we satisfy the heap invariant in the end. If we remove the last 2, we can immediately satisfy the heap invariant with 1 swap. But for learning purposes, I'll simply remove the first one found in our set, which happens to be located at index 0. So we want to remove the 2 at position 0. So how do we remove a node again? So we did a lookup, so we didn't have to do that linear scan, which was nice. And now we swap it with the last node, which happens to be 11. We remove the last node. Now we need to satisfy the heap invariant. So we need to bubble down 11. So we look at 11's children, which happens to be 3 and 2. 2 is smaller, so it's the one we're going to swap with. So swap it in the table and in the tree. Now we are still not in satisfaction of the heap invariant, so look at 11's children being 13 and 2. 2 is smaller, so swap it with 2. And that's it, we're done. The last instruction says to pull, so get the value at the root, which is 2, and swap it with 11. Get rid of the 2, and bubble down 11. So as you can see, we're constantly swap it with 2. And heap invariant, so look at 11's children being 13 and 2. 2 is smaller, so swap it with 2. And that's it, we're done. The last instruction says to pull, so get the value at the root, which is 2, and swap it with 11. Get rid of the 2, and bubble down 11. So as you can see, we're constantly updating our table, but still doing the same operations. So that's how you do quick removals in a priority queue. So guys, thanks for watching, and in the next video, I promise we'll look at some source code for all this crazy stuff that's been going on. The source code can be found at the link provided on this page. Stick around.
Albert School is within the academic world what Edmond de Rothschild is within the world of finance. This is
All right, welcome back everybody. This is part 5 of 5 in the priority queue series, and we're going to have a look at some source code for the priority queue today. So if you want the source code, here's a GitHub link with all the data structures in the series. The priority queue is one of them. Also make sure you've watched parts 1 to 4 so you can actually understand what's going on. All right, let's dive into the code. All right, here we are inside the source code. So notice that inside my priority queue, the types of elements I'm allowing inside my priority queue have to be comparable elements, as we talked about. So if they implement the comparable interface, then we are going to allow them inside our queue. So this is anything like strings, integers, anything with a comparable interface. So let's have a look at some of the instance variables. So I have the heap size. So this is the number of elements currently inside the heap. But then I also have another instance variable, which is the heap capacity. So this is going to be the size of the list that we have for our elements, which may be larger than the heap size is. And this is the actual heap, and we're going to be maintaining it.
Okay, so for this particularly, my priority queue, I wanna implement it so like generic classes, so that I can revise generic classes in C++ because I have completely forgotten generic, and B, so I can just my revision honestly. Right, one function works for all. Template type name T, that's what you do. T, Y, max, T, X, T, Y. T star media, T array. And S. What? Okay, it implements it right here. Like this was a, what's it called? Template function. I don't know. Working on multi type generics, class T, class U. Audio. Pass it in. Max. This is a generic function. This is a generic class. This is a multi-type generic. All right. So you create generics. Oh, I'm kind of sleepy. Anyways, we're gonna look at the code.
As a dynamic list of elements using Java's list. The actual key, and we're going to be making it as a dynamic list of elements using Java's list. Next, for our log event
Is Java list like vectors?
I
I think it is.
elements using Java's list. Next, for our log event rules, I'm also going to keep track of this map. And so I'm going to map an element to a tree set of integers. So these are going to be all positions inside our heap, which we can find this element t.
The fuck is a tree set?
So these are going to be all positions inside our heap, which we can find this element t.
Is collection string we use to store elements in sorted and unique manner. Black tree mass, especially red black tree. Oh, it's a red black tree. Right. A red black tree, right? Obviously, I know what the fuck a red black tree is. Thing comparable MCDB. Set, right? Ascending, red black tree, comparator functor, O login, right? Is there an equivalent way to do the extents? Type T must be comparable. Priority or generation set. C++ doesn't use interfaces like Java, instead use template constraints and operator overlaid to achieve the same behavior. As long as type defines operator, it can be another type defines operator. It can be used in sorted containers like set, map, or with algorithms like sort. Sort if comparable. For this, most explicitly using concepts. But it's C++20, bro. I got like C++4 in some LeetCode type platforms. Because TATV is convertible to whatever. Fuck you.
The list that we have for elements, which may be larger than the heap sizes. This is the actual key, and we're going to be making it as a dynamic list of elements using Java's list. Next, for our log event rules, I'm also going to keep track of this map. And so we're going to map an element to a tree set of integers. So these are going to be all positions inside our heap, which we can find this element t. Alright. Next, I have a few constructors for our priority queue. We can just create a priority queue, by default I'm creating an initially empty priority queue with a capacity of 1. But I also allow you to create a priority queue with a defined initial capacity, which actually is more useful, because I don't have to keep expanding our dynamic list every time. So I would recommend this. Empty priority queue with a capacity of 1.
Public PQ. This one. What the fuck?
But I also allow you to create a priority queue with a defined initial capacity, which actually is more useful, because then we don't have to keep expanding our dynamic list every time. So I would recommend this. But also, even better, is if you know all the elements that are going to be inside your heap, you can actually construct the priority queue in linear time using an operation called heap apply, which I didn't talk about in the slides, but can be very, very useful.
Can be found here.
So this does all the usual setup stuff. Here I'm adding all the elements to the map, but also to heap, and then here's the heap apply process. So we start at about halfway through the heap size, and then we start decreasing, and we sync all the elements. And you're like, wait a second, isn't the sync a logarithmic removal? Well, yes, it is in the general case, but not if we're doing it in this fashion. I really like this paper here just because the heapify operation is quite intuitive why it has this linear complexity.
I watched a really good video of Abdul Bari on this, but I don't think I remember any of it. How long have I been streaming for? I've been streaming for a while, bro. Anyways, like I'm saying, just go to YouTube, look up Abdul Bari heap cartoon. Holy shit. Learning Surah Al-Masallah. What the fuck, bro? No, what I wanna do is Abdul Bari heapify. Oh,
Ankur, there is a typo.
It's a PDF. How do you edit?
Editing at the last minute. With Acrobat, it's all sorted.
I hate this guy. He doesn't even do anything. Only he spent money trying to make himself famous, and then he got famous. It just fucking worked.
The topic for this video is heap. Under this topic, we are going to learn about these things. I will be explaining these things. That is array representation of binary trees, complete binary tree, heap, how to insert and delete in heap, then heap sort. This is one of the important topic. And heapify, this is one of the famous algorithm or a procedure for creating a heap. I'll discuss this one. Then heaps are famous for being used as a priority queue, so we'll learn about priority queues. So these are the subtopics under this heap topic, right? And if you know all these things, then you can understand heap sort, you can also understand heapify and priority queue. Unless you know these things, so directly jumping on this is difficult to understand that. So that's the reason I'm covering all these things. So if you already know a few things, you can skip and go to that topic, right?
And you said I'm gonna do exactly that.
Now before I start, I have to say something. See, I have two courses in Udemy. One is for C++, second one is for data structures. Both the courses are for beginner level as well as advanced level. Means if you already know data structure and C++, you have a lot of things to learn there. And also if you are a beginner, if you have never done any programming, then you can take up C++ course and start learning programming. And both the courses are suitable for academics as well as for interviews. So C++ programming, one course is there, that is from beginners to advanced level. You can learn up to the level of interview, you can crack any interview. Then data structure course using C and C++ and some algorithms are. It's not complete algorithm, it's just a data structure using C and C++, right? And few algorithms are there. So that subject is for academics as well as for cracking job interviews or coding interviews, right? So I have covered all the topics in greater detail, so that will definitely improve your skills. So you can buy those two courses. Those are paid courses, those are not free. And please don't ask for free coupons. The link for those courses is given in the description. You can check the description. And there is a discount code is there. Discount coupon code is there. That is around $10 or $11. So you can click and go to Udemy. And if more discounts are applicable, Udemy will give you that discount. Don't worry about that. If still it can be reduced, it will reduce it. So I suggest you take this course, and by clicking on this link, you go there. So let us start with the topic. First, I will discuss about representation of a binary tree using array. So here I have some examples. This is a binary tree. I have taken the alphabets here so that easy to read. This is a binary tree. And if I have to store it in an array, this is an array I already have taken.
Okay, so wait, what does this course have? Essential C and C++ concepts, array basics, structures, pointers, references, reference, pointer to structure, functions, parameter passing methods, structure as parameter. I don't know. Structures and functions, converting C program to C++. Monolithic program, modular program, structure and functions. Template classes, online C, C++, set up code blocks, settings, dev C++, code blocks, Visual Studio, yada, 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 yada. Right, stack versus heap memory, stack versus heap, ADT, time and space, generalizing, recurrent solution, code recursion, starting global variables, it's code starting global, tail recursion, head recursion, tree recursion. This is so nice. I wish I want to buy this, I think. Power using recursion, let's go power recursion, tail. I don't like maths. Taylor series reminds me of fucking trauma. Horner's rule. Oh god. Fibonacci. NCR Tower of Hanoi. Arrays. Array static versus dynamic. 2D arrays, row major, column major, array ADT. Deleting, linear search, binary search. It really is pretty nice. Student challenge, duplicates, finding parent elements with some K. Max and min, single scan strings. It's so nice. Diagonal matrices. I feel like I should be doing this course, bro. That's what I feel like. So nice. Anyways, I don't have the sort of money right now, so I'm just gonna watch this. Man, this guy's crazy. Heapify. Can I get the Heapify video?
First, I will discuss about
Bro.
Today we're going to learn heap sort. Let's start with some terminology. A heap is simply an ordered binary tree. A max heap has a restriction that the value of the parent nodes are greater than the value of the child nodes. Here's an example of a max heap. We'll make use of a few functions when learning heap sort. First, we have build max heap. This creates a max heap from an unsorted array. We'll also use heapify. This is similar to build max heap, except faster because the part of the array is unsorted. You'll see them. One note. For this video, I'm less concerned with knowing how these methods work, but rather that they exist and when to use them. Once you understand the basics of heap sort, you'll understand these functions are code. Let's get started. We have the following array that tasks to sort. In a nutshell, we'll continuously create max heaps to find the largest item. We'll then move that item into the heap and into a sorted partition. We'll begin by representing our array as a tree. To see how we did that, simply look at the array from left to right and then the tree from top to bottom.
Got it.
Now that we have a tree, let's create our first heap. We assume this is an unsorted array, so we call build max heap. Now that we have our max heap, we know the largest item, 9. We swap 9 with the item at the end of the array, 1. Finally, we remove 9 from the tree and consider it sorted. Looks good so far, except we're back to having a tree, not a heap. This time we call heapify, since only the item 1 is out of place. 1 floats down to the bottom, and the largest number heads to the top. We're back to having a max heap. Let's swap the largest number 8 with the item at the end of the unsorted part of the array, 2. We remove 8 and consider it sorted. Again, we need our heap back, so let's accept. Now that we have our max heap, we assume this is an unsorted array, so we call build max heap. Create our first heap. We assume this is an unsorted array, so we call build max heap. Now that we have our max heap, we know the largest item, 9. We swap 9 with the item at the end of the array, 1. Finally, we remove 9 from the tree.
I don't get
Consider
it.
it sorted. Looks good so far, except we're back to having a tree, not a heap. This time we call heapify, since only the item 1 is out of place. 1 floats down to max heap. Here's the code for heap.
Let's see how this takes in login now. I just can't do it. In the heap file method. How does heap deploy work? What the fuck? Our videos will get flat. Right, let's see this.
Hey, still thinking about joining the 13-day Python using AI bootcamp by AI for Techies?
Oh no, I'm not.
Hello guys, welcome back to the video. So in this video we will see the heap algorithm. So in this case we will be seeing by taking an example of how to heapify a max heap, and this will be very similar to the main heap. So once you solve any one of these, you will understand the other. This is also known as the LeetCode Grind algorithm. You might find it in many blogs as well as some books. And this is the second video of the heap implementation. So I will highly recommend that you watch all our previous videos in this playlist in order to get a complete understanding about the topic. Now let's look at some of the important points before solving the heapify algorithm. Now in this case, if the heap size is let's say n, where we are having n elements, then the range of leaves will be from n by 2 to n minus 1 if it is a zero index array, right? So this I've already explained in the previous video. Therefore, if the leaves are ranging from n by 2 to n minus 1, then the rest of the elements will obviously be internal nodes. Therefore, the range of internal nodes will be from 0 to n by 2 floor minus 1, right? Now let's take an example. This is an example.
Slow the fuck down. Slow the fuck down.
Now let us look at some of the important points before solving the heapify algorithm. Now in this case, if the heap size is let's say n, where we are having n elements, then the range of leaves will be from n by 2 floor to n minus 1 if it is a zero indexed array, right? So this I've already explained in my previous video. Therefore, if the leaves are ranging from n by 2 to n minus 1, then the rest of the elements will obviously be internal nodes. Therefore, the range of internal nodes will be from 0 to n by 2 floor minus ranging from n by 2 to n minus 1, then the rest of the elements will obviously be internal nodes. Therefore, the range of internal nodes will be from 0 to n by 2 floor minus 1, right? Now let's take an example. This is an example. Here we are having some elements 0 to index 6. So now what we will do is here, what are the leaves here? So if you apply the same formula, then you will find that you are having 4 leaves. Okay, and these 3 are the internal nodes. Now if you take another picture, this is a heap. Okay, so this is a max heap. Now in this case, you can see that there are 3 internal nodes, 1, 2, and 3. So the internal nodes will range from 0 to 2, and the leaves will range from 3 to 6. This is index 3 to index 6. Okay, so this is 3, 4, and 5. Okay, so this will be 5, since this is a 0 index element. So 0 to 2 and 3 to 5. So I hope you understood how to find the number of leaves and what are the ranges of internal nodes and the leaves. Once you understand this, let us see something about the heap property. So if you talk about a max heap, then root node should be greater than all the left and the right subtree nodes, and it is recursively true for all the subtrees. And if you talk about a min heap, then the root node should be less than all the left and the right subtree nodes, and it is recursively true for all the subtrees. So both have the same definition. The only difference is that in the max heap, the root will be the maximum element in the subtree or the entire tree, and in a min heap, the root will be the minimum element. Okay, a leaf node always follows the min or max heap property since we have just a single node. So if we just take a tree having a single node, let's say it is 2, then this will be the maximum element as well as the minimum element in this entire tree. So this is the leaf element. Leaf element will always be your min heap, and it will always be your max heap. Both will be correct for that. So in this case, let us take another figure which will be having 2 nodes. Now there is only one leaf which is 3. Is this a max heap? No, because this 2 is a root, and this 2 is not following the max heap property because the left side is greater than this root node. Okay, so if we do a rearrangement and just swap 3 with 2, then is this a heap? Yes, this is a max heap. This was basically a min heap, but we were checking for max heap here. So this was not a max heap, and this is a max heap, since the root element is the maximum in the entire left and right subtree elements. Okay, now let's take another example having 3 nodes. In this case, the root node is this 1. Is this a max heap? No, this is not a max heap. So if we do, let's say, one rearrangement where 2 is swapped with 1. Now is this a max heap? No, this will also not be a max heap because 2 is less than 3, which is its child. Now if we try out other rearrangement number 2, then we will swap 3 with 1. If we do that, then 3 will be going to this root node and 1 will be coming to the leaf. Okay, now is this a max heap? Yes, this is a max heap because these 2 are the leaf nodes, so this will obviously be following the max heap property, and this is the only internal node, and this is the root node, and this is maximum of all the elements in the left subtree as well as all the elements in the right subtree. So I hope you were able to understand this. Now let us quickly move to another example. In this case, let's assume that we are given a heap, okay, and the ith node needs to be rearranged to maintain the heap property. Here we will note that except the ith node, the entire tree is a heap, and just for simplicity, we will take ith node equals to 0th index. In the subsequent videos after this, you will understand how to take how to heapify other index elements. So here I will just be explaining you for the 0th index. Now let's assume that we want to rearrange this ith element in such a way that our max heap property is maintained. Okay. Now here, as I've already mentioned, except the ith node, the entire tree is a heap. Ith node is this one, which is the root node here. Okay. So except the root node, entire tree is a heap. So this left subtree will be a heap. This right subtree will also be a heap. Okay. Now how do we rearrange it so that it will follow the heap property? Well, in order to do that, what we were doing is we were rearranging with the left side or the right side. So let's try that. If we take the maximum of left and right and just swap it with this one, then what will be the result? It will be here 1 will come and here 8 will come, right? So is this a max heap? You can see that this element 8 will be the maximum element in this entire tree, but this doesn't guarantee that this entire tree will be a max heap. Why? Because since you have swapped this 1 with this 8, this subtree might not be now following the heap property. Okay, so it may or may not be following the heap property. We just need to check it. So how do we do that? We will have to now recursively rearrange this element. Now in this case, you see that here 1 is coming. So you will compare with the left side as well as right side. Left side is 3, right side is 4, maximum is 4. So again 4 is greater than this one, so we will have to again swap it back, right? This will be done unless we reach to the leaf node. So now we have reached the leaf node, 1 has come to the leaf. Okay. Otherwise, we will be stopping as soon as we find that this current element is greater than the left element as well as greater than the right element. So what are the stopping conditions in this rearrangement? Here we are starting from the 0th index, so we will stop if we hit a leaf. So if we reach a leaf, then we will stop. The second condition is that if our element, that is the current element, is greater than left as well as current element is greater than right, then we will stop here, saying that in this subtree the current element should be the root and this is the root. Okay, so these are the two conditions of stopping. Now you will see that after doing these two operations, we have done only two operations. Okay, we just swap this one with 8 and again we swap this one with this 4. Okay, and what are the number of levels here? You will find that this is level 0, this is level 1 and this is level 2. Okay, at each level we are doing basically two comparisons with the left side as well as with the right side value, and we are also doing a swap operation. So there are constant number of operations here, and we will be performing at maximum of height of tree number of times these operations. And if we do it recursively, then basically we will be making recursion calls log n number of times. So in this case, since we will be making recursion calls, so the space complexity can go to log n. Okay, and you can also implement it by using a loop. That will be much better. And the time complexity will also be log n because here we have log n number of levels. Okay, so now let us take an example and dry run this entire example to understand. The process of rearranging the heap by comparing each parent with its children recursively is known as heapify. So this is the definition of heapify algorithm, and this word recursively is extremely important. Okay.
Do you ever wonder why the food at a restaurant takes 20 minutes to come to your table? It's because of a system that assigns the
Now in this case, let's assume that we are given a tree and we want to rearrange this ith node. In this case, I will be equals to 0. We want to rearrange the ith node in such a way that it will become a max heap. Okay, so we basically want to heapify this 0th index element. Now how do we do that? In this case, as I've already explained, what we will do is we will just compare it with the left side and right side. So what is our stopping condition? First stopping condition was when we reach a leaf, then we will stop. Second stopping condition was that if our current element is greater than the left side element and our current element is greater than the right side element, then we will stop. Okay. Now in this case, we have element 1 and this is not a leaf node. So first condition is not true. Again, the left side as well as right side both are greater, right? At least one is greater, then we will heapify it. Now we will be taking the maximum of these two elements because the maximum should be at the root. So since this subtree, this left subtree is already a heap and right subtree is already a heap, so the maximum in the left subtree is this node and the maximum in the right subtree is this node because they are max heaps. Okay, we will take the maximum of 14, 10, which is 14, and 14 will be replaced here and 1 will come here. Okay, now I already told you that due to this swap, the heap property of this subtree might be altered. Okay, so we will have to again heapify this recursively. Okay, so now again, is this a leaf node? No, this is not a leaf node, and now we will reach a leaf, then we will stop. Second stopping condition was that if our current element is greater than the left side element and our current element is greater than the right side element, then we will stop. Okay, now in this case we have element 1 and this is not a leaf node, so first condition is not true. Again, the left side as well as right side both are greater, right? At least one is greater, then we will heapify it. Now we will be taking the maximum of these two elements because the maximum should be at the root. So since this subtree, this left subtree is already a heap and right subtree is already a heap, so the maximum in the left subtree is this node and the maximum in the right subtree is this node because they are max heaps. Okay, we will take the maximum of 14, 10, which is 14, and 14 will be replaced here and 1 will come here. Okay, now I already told you that due to this swap, the heap property of this subtree might be altered. Okay, so we will have to again heapify this recursively. Okay, so now again, is this a leaf node? No, this is not a leaf node, and now we will check with the left side as well as right side. Both left and right are greater. Okay, if at least one is greater, then we will heapify. So both are greater here. Now we will be taking the maximum of 8, 7. 8 is greater, so 8 will be swapped here, 1 will come here. Now again, we will be heapifying this subtree. Okay, so for this subtree, 1 is the root. Now again, what we will do is 1 is a leaf. No, 1 is not a leaf, and this left side as well as right side both are greater. Okay, actually if at least 1 is greater, we will do the heapify. Here both are greater. Again, we will take the maximum element. Maximum is 4. 4 will be replaced here. 1 will come here. Now we will see this element. So this element 1 is a leaf, so we will stop here, right? And whatever is the resulting tree will be the max heap. In this case, the root node is 14. Again, this is 8, this is 4, and this is 1. If you check it, then you will find that this is a max heap. So this is the entire heapify algorithm. Here, the important thing to note is only one index, that is only the ith index element will not be following the heap property, and the rest of the elements will be following the heap property. And that is why we will be applying heapify to the ith element in order to make this entire structure into a heap structure. Okay. Now let us see the algorithm here. So once you have understood the dry run, it will be just a cakewalk in order to understand this max heapify algorithm. So we are given an array. Array will be the representation of the given heap, and this is the ith index which we want to heapify. Now we will find the left side, we will find the right side, which is at 2i plus 1 and 2i plus 2. And now we will check if there exists a left child. Okay, so left child should be within bounds of the heap size. So this is nothing but the array size, a dot heap size. Now once left child is within bounds, then it is sure that ith element is not a leaf element. Okay, and the left child element should be greater than the ith element. Now let me take an example, then that will be better. Okay, let's take a variable largest which will be containing the largest element. That is the largest element index. Now in this case, let's assume that we are talking about this ith index. Okay, so it is having a left side, yes, and a at l is greater than a at I. Well, that is also true. So the largest will be storing the index of l. So largest will be updated with l. Okay. Otherwise, if this was not true, then largest will be storing the value I. But in this case, this is true. Okay. Now we will be checking for the second condition. Now we will check if the right side exists. So if right side is within the limits, that is within the bounds of the array size, then right side will also exist. And now if right side is greater than the current largest element, which is this 3, that is array at l. Okay. So array at l is basically 3. Now array at largest, which is this 3, is less than the array at r, which is 4. So again, the largest will get updated. So this will now be storing index r. Okay. And now we will check if the largest is not the current element. If it is not the current element, then obviously there is an element which is aligned to the subtree either on the left hand side or on the right hand side, which is having a higher value than this ith element. And so we will have to swap the element and again recursively call the max heapify algorithm, right? So in this case, 4 will be swapped with this 2, and again we will be calling max heapify on this 2. And on the next time, since this 2 will be a leaf node, this if conditions will be skipped and this largest element will remain as the ith element because this l will be out of bounds, this r will also get out of bounds. Okay, because I is the leaf node. Therefore, this largest not equals to I will be false. And here we will stop. So this is how we stop at the leaf node. Otherwise, let's say if your figure was something like this, 4, 2, and 3, and if this was your ith element, then obviously your largest would be pointing to index I, because when you are comparing here, then L will be obviously in bounds, but A at L greater than A at I will be false, and so largest will be given value I. Again, when you compare with R, which is this value 3, then A dot heap size, that is it will be within the limits, and array at R, which is the value 3, greater than the array largest, which is 4, will be false, and so largest will still remain to be I. Okay, and this condition will not run, and therefore we will stop. So these were the two stopping conditions. First, we will stop if we hit a leaf, and second condition was that if the current element is greater than R and the current element is greater than L. If the current is greater than both right and left child, then we will stop here. So I hope this maxify algorithm was very much clear to you. Now in this case, it is pretty simple to understand that the time complexity will be log n, because this is the height of the tree, and the space complexity can also go to log one index, that is only the.
Bro, what if I still don't get it. I feel like this is, he's like skipping cases. Can you explain how heapify takes O(n) time complexity from unsorted array take O(n) time? In inserting each element into a heap individually would take O(n) log n. All elements in the array need the same amount of work to heap on building a heap from bottom of heap if it's the branch of the structure of the binary heap. Last non-leaf node, go upward to the root. That's what I'm trying to say. You start from the last. Okay, that makes so much more sense. Because you need to ensure that the bottom trees themselves are max heaps, right? Start from the non-leaf node, go upward to the root node. At each node, you sift down, aka heapify, to maintain the heap property. The last non-leaf node is at index n by 2 minus 1. It's at index n by 2. Right, that's correct. That's correct. Okay. Nodes near the bottom have very little height, less work. Moreover, there are fewer of them. So the work is not O(n) into O log n, because more nodes with less height, maximum height node can sit down proportional to its depth from the bottom. Total time calculation, we can sum the work done by h with the height of tree that n by 2 raised to the power h nodes at height h. N by 2 raised to the power h at height h, and is n bond to the power h node. Yeah, okay, just 2 raised to the power h. Each node takes OH time to heapify. Total cost is summation of h equals 0 to log n by 2 is for h, which evaluates to O(n). Math works out because high cost nodes are very few. Heapify is O(n) using bottom construction. Time complexity, heap sort, extraction. You're right. Building the heap takes O(n) and extraction takes O(n). So heap sort is pretty nice if you just want the greatest element, because what the fuck? No, it's not. It still just takes O(n) time. Man, algorithms are fucking beasts.
ith index element will not be following the heap property, and the rest of the elements will be following the heap property. And that is why we will be applying heapify to the ith element in order to make this entire structure into a heap structure. Okay. Now let us see the algorithm here. So once you have understood the diagram, it will be just a cakewalk in order to understand this max heapify algorithm.
Swab AI A largest.
So we are given an array not equals to I will be
Build.
Got it now. I got it now.
End up seeing that the complexity boils down to convergent series, and that's why we get a constant in say it's linear time. But in general, this isn't what you might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just.
Right, I'm gonna take a little break now. I've been building my project in the morning and I did this for DSA. I mean, if I feel like it, I'm gonna go through a few questions, but you might not know this, but we just finished a few topics. So like if I open the website, a few topics are just learning heap. If I like look at this, introduction to priority queues using binary heaps. See, min heap and max heap implementation. There's a question you can solve. Implement min heap with the following methods. Right, we can do that question later. I can do that question later, but right now my eyes are gonna kill me. So I'm gonna end the stream right here, and thanks for joining in. Is there someone in chat? No more than chat, but this was a really nice session. Although I did have to persevere through because my eyes are fucking killing me. And think I'm done for the day. I might be, or I might not. If my eyes feel better, I'm gonna do a few more questions. I wanna get to graphs and like, right, I wanna cover the breadth of the topics first now so that I can at least, well, I can say I know what a topic is, right? Like if I do 4 or 5 questions from priority, I'm pretty sure I'll start getting it, right? I see this question. This is just implementing all the functions. So it's initialize heap, insert, change key, extract min is empty. So it's a really nice way to get to learn all of this. And once I'm done with this, so let's just take a look at this. So there's heaps, and then there's greedy algorithms, binary trees, binary search trees, graphs, dynamic programming, tries, and strings. Strings, again, I think I've done strings basic and medium is at step 5, and strings, I guess, advanced, hard problems. Yes, that's the last step. But, that's what I'm going for. Now you get it? Man, I feel like I've done a lot of this. Although I'm at step 9 and I haven't even completed that, and there's 18 steps. And step 15 and 16 are like more than 100 questions. There's 110 questions just in step 15 and 16, but regardless. So you see what I'm going for now. So I'm gonna check out for today. Thanks for joining in if you did, and if you did not join in, well, you can comment if you are watching afterwards. That's gonna be interesting to see if someone comments. And I'm gonna see you guys in my next stream. Thanks for joining again. I gotta stop streaming.